There is a clock somewhere near you right now, maybe on a nightstand, maybe glowing faintly on a phone screen turned face down. And somewhere else, tonight, on the side of a mountain, in the cold, thin air above the world, there is another clock. They look the same, they tick the same, and yet quietly, without either of them knowing it, they are not keeping exactly the same time. If this feels like a good place to rest tonight, you are welcome to stay. Let's drift for a while and see where this quiet little fact takes us. Because that clock on the mountain is not broken, it is not wrong, it is simply living in a very slightly different version of time than the one beside your bed. Physicists have confirmed this using atomic clocks so precise they can measure a difference of time smaller than a heartbeat, smaller than a breath, smaller than anything the human body could ever notice on its own. And yet the difference is real. It has been measured. It has been recorded. Two clocks separated only by height, drifting apart in time, by fractions so small they seem almost imaginary, and still somehow true. It is strange to think about. Time, the thing we trust the most, the thing we build our whole lives around, waking and sleeping and waiting and remembering, is not quite as steady as it feels. It bends, ever so slightly, under conditions most of us will never notice, in places most of us will never stand. And yet it happens here too, in this room, in this very moment, though far too small to sense. Maybe that is enough for tonight, just to know that time is a little softer than it looks, a little more alive than it seems. There is something similar that happens inside the mind long before anyone ever measured a mountain clock. You may have felt it yourself, a single afternoon that stretched on for what felt like days, or a whole year that seemed to slip by in the space of a breath. Psychologists often note that the brain does not experience time evenly. It stretches some moments and compresses others, depending on attention, on emotion, on how much the mind is asked to notice. A quiet evening like this one, for instance, tends to feel long in a gentle way. Nothing urgent is happening. Nothing is asking to be remembered in detail. So the mind loosens its grip on the clock, and time begins to feel wider, softer, easier to sink into. It seems that stillness itself changes how time is felt, even if it cannot change how time actually moves. Researchers who study memory and perception have found that the density of experience shapes the sense of duration. A day full of new streets, new faces, new sounds tends to feel long while it is happening and short in memory. A day spent quietly doing very little tends to feel the opposite. Short while it is happening, and yet strangely longer when remembered because so little of it blurred together. It is almost as though the mind keeps two different clocks of its own, one for living through a moment and one for looking back on it later. And neither of those clocks matches the one on the wall. Maybe this is part of why nights like this feel the way they do, not urgent, not rushed. A kind of soft suspension where the ticking of an actual clock somewhere in the house seems to matter less and less. There is a reason scientists became so interested in questions like these. Not just how the mind bends time, but whether time itself out in the universe might bend in a similar way. It began quietly with a question. A young man wondering what it might be like to travel alongside a beam of light. What would he see? What would happen to time if he could somehow keep pace with something moving that fast? It was not a loud question. It was not asked to impress anyone. It was simply a thought turned over slowly, the way a person turns over an idea late at night when the rest of the world has gone quiet. And that quiet question would eventually lead somewhere no one expected. A place where clocks on mountains and clocks in bedrooms are only the smallest hint of something much larger. Something we understand a little more of now, though, certainly not all of it. Scientists are still exploring the edges of it even today, but that is a thread for later. For now, it is enough to simply notice the strangeness sitting quietly beside you tonight. That time, the most familiar thing in the world, might not be quite as simple as it feels. That somewhere above you, a little higher up, time is moving just slightly differently than it is right here in this room, around your shoulders, around your breath. Let that thought settle for a moment. There is no need to hold on to it too tightly. It will still be here waiting quietly whenever you're ready to follow it a little further into where it leads. Somewhere in the quiet of a night like this, there is a question worth turning over slowly. Why does time feel different depending on where the mind happens to be standing? A single hour spent waiting for something can stretch until it feels endless. And yet an entire evening spent doing something absorbing can vanish so completely that when it ends, a person might wonder where it went. It seems that the mind is not simply keeping time, it is constantly deciding how much of it to notice. Neuroscientists have observed that this sense of duration is closely tied to something called novelty. When the brain encounters something new, an unfamiliar street, an unexpected sound, a face it hadn't seen before, it works a little harder to take it in. It lays down more detail, more texture, more memory. And afterward, when that stretch of time is remembered, it feels longer simply because there is more inside it to recall. A routine evening, by contrast, offers very little for the mind to hold on to. The same chair, the same quiet room, the same soft light. There is nothing new to record, so very little gets stored. And so strangely, an evening like this one might feel unhurried while it is happening, and yet barely leave a trace once it has passed. This may be part of why childhood summers are remembered as long golden stretches, while adult years seem to move faster with each passing season. A child's world is almost entirely new. Every day holds something unfamiliar, a new game, a new word, a new shape of cloud never noticed before. The mind, busy cataloguing all of it, experiences those days as vast. But as a life goes on and the world becomes familiar, days begin to resemble each other. There is less for the mind to record, and so time remembered afterward seems to move more quickly. There is something quietly comforting in that thought. It isn't that time itself is speeding up, it's that the mind over the years has simply learned the shape of things. Attention plays its own part in this as well. Psychologists often note that when a person is deeply focused on something, fully absorbed in it without noticing the outside world at all times, seems to fall away almost entirely. Painters describe it. Musicians describe it. So do gardeners and cooks and anyone lost in a task they love. Hours pass and it feels like minutes. This state has been studied closely, and researchers have found that during it, the usual internal sense of time monitoring seems to quiet down. The mind isn't checking the clock because it isn't asking to be anywhere else. Boredom does the opposite. When there is nothing to hold attention, the mind turns its focus back onto itself and onto the passing of time directly. Each minute becomes noticeable because there is nothing else for the mind to notice instead. This is why 5 minutes of waiting can feel far longer than 5 minutes spent absorbed in something gentle and engaging. Perhaps that is one small reason nights like this one feel the way they do. Not boring, not searching for something to fill the space, but not urgently focused either. A kind of soft middle place. Attention loosened but present, which may be exactly why time right now feels slow in the kindest possible way. Emotion changes the shape of time as well, though not always gently. Fear in particular seems to stretch a moment far beyond its actual length. People who have lived through sudden danger, a car losing control, a fall, a flash of unexpected shock often describe the seconds slowing down almost impossibly. Some researchers believe this happens because the brain under threat begins recording far more detail than usual, laying down memory more densely than it would in a calm moment. Afterward, when that memory is replayed, it feels like it lasted far longer than the clock would agree to. It is a strange kind of protection if that is truly what it is, as though the mind sensing danger tries to give itself more time to think, even if the extra time exists only afterward in memory and not in the moment itself. Tonight holds none of that urgency, of course. If anything, the opposite is happening. As the body settles and the breathing slows, the nervous system quiets its usual sense of alertness. And it may be that this quieting itself changes the experience of time, stretching these minutes into something softer, wider, less measured than an ordinary hour of the day. There is another layer to this as well, one that lives closer to the body than the mind. Body temperature appears to have a small but real influence on how time is perceived internally. Some studies indicate that when the body runs slightly warmer, internal timing can feel like it's moving faster, and when the body cools, that internal sense can slow. It is only a small effect, subtle, easy to miss, but it hints at something worth noticing. That the sense of time is not only a mental experience, it is something felt through the whole body temperature and heartbeat and breath, all quietly contributing their own small signals. As the night goes on and the body begins its natural drop in temperature, preparing itself for deeper rest, perhaps this is one more quiet reason time feels like it's loosening its grip. Not just the mind slowing down, but the body itself gently, wordlessly joining in. There is one more thread worth following before moving on. Dreams. Anyone who has ever had a dream that seemed to unfold over hours, entire days, even only to wake and realize just a few minutes had passed, has brushed up against one of the strangest corners of time perception. The brain during certain stages of sleep appears to construct entire sequences of experience compressed into a fraction of their felt length. Some researchers have proposed that dream time is less like a clock and more like a story built, instant by instant, stretched and folded however the mind sees fit. This suggests something rather beautiful, if quietly so. That time, at least, the way it's experienced was perhaps never a straight, steady line to begin with. It bends around attention. It stretches with fear. It compresses with routine. It folds entirely during sleep. The clock on the wall may move evenly, tick by even tick, but the mind living alongside it has never quite agreed to match its pace. And that brings the mind back gently to where this evening began. To a mountain and a clock and a very small difference in time that had nothing to do with attention or memory or dreams at all. A difference measured not by feeling but by instruments so precise they could catch a fraction of a second sliding out of place. Because if the mind can bend time on its own quietly and visibly every single day, then perhaps it isn't so strange after all that the universe itself might do something similar. Not through memory, not through emotion, but through something far stranger hiding in the way light moves and clocks tick and space itself seems to stretch. That was the question a young man once asked lying somewhere quiet, much like this. A question that would eventually reach far beyond dreams and memory and mountains into the very fabric holding time together. For now, let that thought simply rest here unhurried. The way everything else has settled tonight, there will be time enough to follow it further. There is a particular kind of stillness that settles over a mind late at night when the world outside has quieted enough for a single thought to be turned over slowly without interruption. It was in a stillness something like that more than a century ago that a 16-year-old boy first asked himself a question that seemed almost like a daydream. What would the world look like? He wondered if he could travel alongside a beam of light. It sounds like the kind of thought a person might have and then let go of by morning. But this one didn't let go of him. Researchers who have studied his notebooks and letters have found that this single imagined journey stayed with him for years, quietly, patiently, the way certain questions do when they touch something true. If he could somehow move at the same speed as light, he reasoned then, the light wave beside him would appear frozen, motionless. A ripple caught in place, neither rising nor falling, but that felt wrong. Light, as far as anyone understood, it was never supposed to stand still. It seemed that something in this picture didn't fit together, though it would take years of quiet thought before he understood exactly what. There is something gentle in imagining a young mind returning again and again to a single impossible picture, not because he was trying to prove anything, but simply because the question wouldn't let him rest until it had been answered honestly. By the time he was in his 20s, working a modest job, far from any university, spending his days reviewing patent applications, that early question had grown into something larger. He had come to a conclusion that felt on its surface almost absurd. The speed of light, he proposed, is not like the speed of anything else in the universe. It doesn't change depending on how fast you are moving or which direction you're moving in. It stays exactly the same always for every observer, no matter their motion. This idea alone might not sound like much, but it carries something enormous hidden quietly inside it. Because if the speed of light truly never changes no matter how fast someone is moving toward it or away from it, then something else has to change instead. And that something, strange as it sounds, turns out to be time itself. It helps maybe to imagine two people, one standing still on a quiet platform, the other moving past on a very fast train, so fast it approaches a meaningful fraction of the speed of light, though. Of course, nothing on Earth moves quite that quickly in reality. If both of them could somehow measure the speed of the very same beam of light, they would each get the exact same number. Not almost the same, not close, exactly the same. And the only way that could possibly be true, if you think about it slowly, is if time and space themselves are behaving differently for each of them. The one in motion would need to experience time passing just a little more slowly, so that the math of light speed still comes out equal for both. It seems that nature, rather than bending the speed of light to fit our expectations, simply lets time bend instead. This became known eventually as special relativity, not because it applies only to special situations, but because it was at first a special or limited version of a much larger idea he would develop later. At its heart is something surprisingly calm to sit with. There is no single universal clock ticking away somewhere above the universe, keeping the one true time for everyone. Each observer carries their own version of time with them, shaped quietly by how they are moving through space. It is a strange thing to imagine lying still in a room like this, that somewhere right now, someone on an airplane is aging in the most literal and measurable sense at a very slightly different rate than someone standing on the ground below. Not because of anything mystical, simply because motion itself has a quiet effect on time, one far too small to feel but real enough to measure and real enough eventually to prove. For years this remained mostly a thought. An elegant piece of mathematics admired by a small circle of physicists, but without any obvious way to test it. Evidence suggests that it wasn't taken entirely seriously by the wider scientific community, at first not because it seemed wrong, but because it seemed so far removed from anything anyone could actually observe. The differences it predicted were unimaginably small at the speeds available to human beings at the time. A person on the fastest train or the fastest ship would experience a difference in time so slight it could never have been detected with the instruments that existed then. And yet the idea sat quietly waiting, the way some of the truest ideas in science often do, waiting patiently for technology to eventually catch up to imagination. What made this idea even stranger and even more beautiful in its own quiet way is what it implied about the nature of now. We tend to imagine the present moment as something shared, as though everyone everywhere is standing together on the same single point of time, experiencing this exact instant together. But if each observer's time can shift slightly depending on their motion, then the very idea of a single shared now begins to soften at the edges. What we understand so far suggests that two people moving differently through space might not entirely agree on which events happened at the same time at all. That thought alone is worth sitting with for a moment, not to solve it or explain it further just yet, just to let it rest there quietly the way a slow question rests in the mind before sleep. That perhaps the present moment was never really one single thing to begin with, that it might look slightly different depending on where you're standing and how fast you're moving through the dark. None of this changes how the night feels right now. The room is still quiet. The breathing is still slow. But somewhere behind these simple ordinary minutes there is this much larger idea, humming softly in the background, mostly unnoticed, the way certain truths tend to hum quietly beneath the surface of ordinary life. It would take years before this idea could be tested directly, before scientists found ways to send atomic clocks flying through the sky, or watch tiny particles live longer than they should. But it began here, with nothing more than a young mind imagining what it might feel like to ride alongside a beam of light and refusing to let the question go until it revealed something true. There is a quieter layer to this still waiting just beneath the surface, one that has less to do with imagining light and more to do with something as simple and familiar as motion itself. There is a simple way to picture what happens when something moves very fast, one that physicists have used for generations, and it begins with something as ordinary as a beam of light bouncing between two mirrors. Imagine a clock built not from gears or hands, but from a single flash of light. It bounces from a mirror on the floor to a mirror on the ceiling and back again, and each round trip counts as one tick. If this little clock sits perfectly still, the light simply moves straight up and straight down, over and over in a clean, quiet rhythm. But now imagine that same clock placed inside something moving. A train perhaps gliding forward at tremendous speed. From the point of view of someone standing outside watching the train pass by, the light inside no longer travels in a simple straight line. It has to move diagonally, tracing a longer path as it chases the ceiling mirror, which has shifted forward along with the train. Here is where the strangeness begins. Since the speed of light never changes, no matter how fast the train is moving, that longer diagonal path has to take a little more time to complete. Which means from the outside observer's perspective, the moving clock ticks more slowly than it would if it were standing still. Researchers have found that this isn't a trick of perception or a flaw in the light clock itself. It applies to every kind of clock, every kind of process, every kind of change that unfolds inside a moving object. Atoms vibrating, hearts beating, thoughts forming, all of it quietly slows down by exactly the same proportion according to anyone watching from outside that motion. It's worth sitting with that for a moment. Not because it needs to be solved right now, but because it's a rare kind of idea, one that asks nothing of you except to imagine it slowly, the way you might imagine snow falling in a place you've never been. For someone actually riding inside that fast-moving train, none of this would feel unusual at all. Their own heartbeat would feel perfectly normal. Their own thoughts would move at their usual pace. The strangeness only appears when comparing their experience to someone else's, someone standing on the ground watching them move past. Time itself hasn't broken, it has simply stopped being something everyone shares equally. At the speeds available in ordinary life, walking, driving, even flying in a commercial plane, this effect exists, but it is almost impossibly small. Smaller than a fraction of a heartbeat spread across an entire lifetime. It seems that our everyday experience of motion sits so far below the threshold where this becomes noticeable that we never sense it at all. The difference is there, it's simply too quiet to hear. But nature offers other places to look, places where speeds climb high enough for this quiet effect to become measurable. Deep underground and in a few enormous circular tunnels built specifically for this purpose, tiny particles are accelerated to speeds that come remarkably close to the speed of light itself. Scientists are still exploring the finer details of what happens inside these enormous machines, but one thing has been confirmed again and again. As these particles approach light speed, their internal clocks, in a sense, slow down, exactly as the old light clock thought experiment predicted. There is something almost tender about that. An idea imagined quietly by a young man alone with his thoughts, decades before any machine existed capable of testing it, turning out to match reality with extraordinary precision down to fractions of a percent. The effect grows the closer something gets to the speed of light, though never in a simple straight line. Evidence suggests that the relationship curves sharply upward as speed increases almost lazily at first, and then more and more steeply the closer an object comes to that final unreachable limit. Halfway to the speed of light, time slows only slightly, but at 99% of that speed, the slowing becomes dramatic. And as an object's speed edges closer and closer to 100% time, for that object from an outside perspective seems to approach something close to a complete stop. No object with mass has ever been pushed all the way to light speed itself. What we understand so far suggests that doing so would require an infinite amount of energy, which makes light speed less like the top of a hill and more like a boundary. The universe simply won't allow anything solid to cross. Only light itself and other things without mass get to travel at that particular pace, existing in a way entirely outside the usual flow of time altogether. It's a strange, quiet thought to hold on to, that light in some sense doesn't experience time passing at all, that from light's own perspective, if it could have one, the beginning and end of its entire journey across the universe might happen in the very same instant. None of this is something a person can feel directly. There is no dramatic sensation attached to moving fast, no internal alarm that rings out as time bends. The body simply continues unaware exactly as it always has. It's only when comparing two different points of view, one in motion, one still, that the difference reveals itself at all. Perhaps that's part of what makes this so easy to sit with quietly at night. It isn't asking anything of your senses. It isn't something you're meant to feel right now in this room, in this stillness. It's simply something true humming along quietly in the background of the universe, whether anyone happens to notice it or not. There is another question that grows naturally out of this one, and it moves in a slightly different direction. Speed isn't the only thing capable of bending the pace of time. There is something else far more familiar, far closer to daily life, pressing down gently on everyone and everything all the time. It has been sitting quietly beneath every step you've ever taken, every night you've ever slept without you ever noticing it was doing anything to time at all. Above your head right now, more than 12,000 miles up, a small satellite is quietly circling the Earth. It moves faster than any train or plane could ever manage, faster than anything built on the ground has any reason to move. And it carries with it, tucked inside its frame, one of the most precise instruments ever built. An atomic clock ticking away with extraordinary steadiness, far more accurate than anything found in an ordinary home. That clock has a very particular job. It helps a phone somewhere down here know almost exactly where it is. This is the quiet foundation of the system many people use every day without a second thought. The network of satellites that makes it possible to find a street, a restaurant, a way home in the dark. Researchers have found that this entire system depends almost entirely on getting time exactly right. A timing error of even a few billionths of a second could shift a location on the ground by several feet. A slightly larger error, and the whole system would slowly drift into uselessness. Here is where something rather beautiful happens quietly high above the clouds. Those satellites are moving at roughly 9,000 miles an hour, fast enough that the effects of speed on time, the very same effects discussed earlier tonight, become measurable in a very real, practical way. Moving that quickly, their onboard clocks tick very slightly slower than identical clocks resting on the ground. Left alone, this alone would cause the satellite clocks to lose about 7 microseconds every single day. A tiny amount, and yet over time more than enough to throw off a navigation system meant to be accurate down to a matter of feet. But speed isn't the only thing acting on those clocks. They are also sitting much farther away from the Earth than anything on its surface, floating in a place where gravity's pull is noticeably weaker than it is down here. And since gravity slows time, being farther from it has the opposite effect. It seems that the weaker pull of gravity at that altitude actually speeds those clocks up, and by a larger amount than their speed slows them down. The gravitational effect adds about 45 microseconds each day working in the opposite direction from the speed effect. Add the two together, and the satellite's clocks run fast overall by about 38 microseconds every single day compared to a clock resting quietly here on the ground. That might sound impossibly small, and in most parts of life it would be. But evidence suggests that if left uncorrected, this small daily drift would cause positioning errors to grow by several miles within just a single day. A tiny mismatch in time multiplied across the vast distances light and radio signals travel becomes something surprisingly large very quickly. So quietly, engineers built the correction directly into the system itself. Each satellite's clock is deliberately calibrated before launch to tick very slightly slower than an ordinary clock on the ground, precisely enough to offset the extra speed gained once it reaches orbit. It's a strange kind of foresight, engineering something to be intentionally wrong in one very specific calculated way, so that once it experiences the true conditions of space it becomes exactly right. There is something quietly moving in that. An idea born from a young man's imagination more than a century ago, tested slowly over decades in laboratories and towers and airplanes, eventually became something so trusted, so essential that it now sits quietly encoded into machinery circling the planet, keeping ordinary daily life running smoothly, whether or not anyone looking at a map ever stops to think about why it works as well as it does. It's worth pausing on that thought for a moment. Every time someone follows a set of directions to somewhere new, a small invisible correction for the bending of time confirmed by physics calculated with extraordinary care is quietly at work in the background making that possible. Time dilation isn't only something happening billions of miles away, or something reserved for particles too small to see. It's happening constantly right now in the satellites drifting slowly overhead, keeping pace with a planet that never stops turning beneath them. There is a quiet kind of comfort in imagining those satellites up there tonight, gliding silently through the dark, carrying their small, precise, deliberately imperfect clocks. Somewhere among them, invisible against the stars, both kinds of time distortion, the stretching from speed and the quickening from distance are balancing each other out this very moment, allowing ordinary things down here, a phone glowing softly on a nightstand, a car navigating a quiet street to work as smoothly as they do. It seems strange in a gentle way that something built to help people find their way through unfamiliar streets relies so completely on an idea that once seemed like nothing more than an impossible daydream. A young man wondering what it would feel like to ride beside a beam of light, and more than 100 years later that same daydream quietly guiding satellites through the sky above sleeping cities, correcting for a version of time, bending too subtle for any person to ever notice directly. Once this system was fully understood and confirmed, working exactly as the equations had predicted, it opened a door towards something even closer to home. Because if satellites in orbit thousands of miles above the ground show measurable effects from both speed and gravity working together, then perhaps something similar might be found somewhere far less distant. Somewhere not among the stars at all, but instead high above the ground in an entirely different, far more familiar way. Speed was only the beginning. There is something else quieter, more constant that has been shaping the pace of time since before there were any clocks at all to measure it. It never announces itself. It simply presses down gently and endlessly on everyone and everything. It is the very thing holding you against the mattress right now, the same invisible pull that has kept the ocean in its basin and the moon in its orbit. Gravity. For a long time, gravity was understood the way an apple falling from a tree suggests it should be. A force reaching out from one mass to another, pulling them together across empty space. It was a beautifully simple idea, and it worked remarkably well for centuries. But there was always something slightly unsatisfying about it, a question tucked quietly underneath the equations. How exactly does gravity reach across empty space to pull on something at all? What is it actually doing? The answer that eventually emerged came once again from a mind willing to sit with a strange little thought experiment rather than rushing past it. Imagine a person standing inside a closed elevator with no windows, unable to see outside. If that elevator was sitting still on the surface of the earth, they would feel their own weight pressing down against the floor in the usual way. But now imagine that same elevator instead floating far out in empty space, entirely free of any planet's gravity, being pulled steadily upward by a rope accelerating faster and faster. Here is the strange part. The person inside would feel exactly the same pressure against their feet in either case. There would be no experiment they could perform standing inside that sealed box to tell whether they were resting on a planet or being accelerated through empty space. The two situations physicists came to realize are not just similar. In a very deep sense, they are the same thing. This became known as the equivalence principle, and it turned out to be one of the quieter, more elegant doors leading toward general relativity. If acceleration and gravity are in this sense indistinguishable from one another, and if it was already understood that acceleration bends the passage of time, then something rather remarkable follows naturally. Gravity itself must bend time as well. Must. It's worth letting that settle for a moment. Not as something to memorize, but simply as an image. A mass like a planet or a star doesn't just pull on things around it the way a hand might pull a string. It gently reshapes the space and time surrounding it, the way a heavy object resting on a soft mattress creates a slight curve in the fabric around it. Anything moving nearby doesn't feel an invisible hand reaching out. It simply follows the natural curve of the space it finds itself in, and time follows that same curve. Closer to a large mass where gravity is stronger, time itself moves a little more slowly. Farther away, where gravity's pull grows fainter, time moves a little more quickly. Not because clocks are behaving strangely, because time in that place quite literally passes at a different pace. For years, this remained largely theoretical, elegant on paper, but far too subtle to observe directly with the instruments of the time. It wasn't until 1959 that two physicists working with a tower just 70 feet tall found a way to test it. By sending a very particular kind of radiation from the bottom of that tower to the top, they were able to detect an extraordinarily small shift, one caused by nothing more than that slight difference in height, and therefore that slight difference in gravitational pull. The experiment confirmed what the equations had quietly predicted all along. Even over a distance smaller than most houses, gravity was in fact bending time. Decades later, researchers found a way to make this effect almost unbelievably tangible. Using two of the most precise clocks ever built, they placed one of them just a single foot higher than the other, roughly the height of a stack of books. And they were able to measure directly that the higher clock ticked forward very slightly faster than the one beneath it. A difference caused by nothing more than 1 foot of elevation, and the almost imperceptibly weaker pull of gravity found there. There is something quietly moving about that, not because it changes anything about how a night like this actually feels, but because it means that even inside this very room the air near the ceiling is in some infinitesimally small way aging just a touch faster than the air near the floor. Time is not a single uniform river flowing evenly through a house. It is closer to something layered, subtly uneven, shaped by the very shape of the space it moves through. The effect grows enormously stronger near objects with far greater mass than a planet like this one, near an incredibly dense star, or closer still to something even more extreme. The slowing of time caused by gravity becomes so pronounced that it is no longer measured in fractions of a second, but in something closer to entire stretches of ordinary experience. It seems that gravity in its most extreme forms doesn't just gently nudge time, it can stretch it almost beyond recognition. There is a certain strange comfort in imagining that this same gentle force, the one keeping your body settled here still and heavy, sinking a little further into rest with every breath, is the very same force capable of doing something this profound elsewhere in the universe. The pull that is helping this night feel slow and safe is in truth the exact same phenomenon capable of bending time itself into unrecognizable shapes given enough mass and enough patience. None of this needs to be understood all at once. It can simply sit here quietly the way most true things do once you stop trying to hold them too tightly. There is a quieter layer to this still waiting beneath the surface, one that most people never consider. Because this isn't only a theory confirmed in laboratories and towers built specifically to test it. It is a piece of physics quietly at work above your head every single day, inside something far more familiar than a tower or a falling apple. Something almost everyone carries in their pocket without ever thinking about the strange, careful mathematics keeping it accurate. High above the Earth, roughly 250 miles up there, is a place where the ordinary rules of a day and a night stop making much sense. 16 sunrises happen there in the space of what would be a single day on the ground. The people who live there for a while, floating rather than standing, tend to describe time itself as feeling strange, untethered, difficult to hold on to in the usual way. One of them, an astronaut named Scott Kelly, spent nearly a year aboard the International Space Station, almost a full year drifting in orbit circling the planet again and again, while his identical twin brother Mark, also an astronaut, remained down here on the ground. What makes their story so quietly remarkable is not simply the length of that mission. It is what happened afterward, when scientists had the rare chance to compare two people who began life as close to identical as two humans can be. Researchers found that Scott returned to Earth having aged very slightly less than his brother. Not years, not months, not even a full second. The difference came out to only a few milliseconds, an amount of time so brief that no human sense could ever notice it directly. And yet it was measured, it was documented. Two brothers born only minutes apart all those years ago had drifted however faintly out of step with each other, simply because one of them had spent months moving quickly through space, farther from the pull of the Earth than the other. It happened for two quiet reasons, working together rather than against each other. Being in orbit means moving at extraordinary speed, thousands of miles an hour, fast enough for the effects of motion on time to become just barely measurable. But being in orbit also means being slightly farther from the Earth's mass, where its gravitational pull is a little weaker. And since gravity slows time down, being farther from it should in a sense speed time up in comparison. These two effects pull in opposite directions, and for the particular height of the space station the balance tips only very slightly towards speed, winning out. Which is why Scott, despite being farther from Earth's gravity, still ended up very slightly younger than his brother, rather than older. It seems that even something as vast and complicated as spaceflight comes down in the end to which one of two extremely subtle effects tips the scale a little further. There is something tender in imagining this. Two brothers sharing the same birthday, the same face, the same childhood memories, and yet carrying after that mission a difference between them, too small to see, too small to feel, but real enough for scientists to measure and record. Not a difference in who they are, only the smallest possible difference in how much time has quietly passed through each of their bodies. It's the kind of detail that seems almost impossible to imagine happening to real people in a real family and not simply inside an equation. And yet studies indicate that similar effects have been confirmed again and again using far more precise instruments than a human lifespan could ever measure directly. In the early 1970s, scientists carried out an experiment that in its own quiet way feels almost playful. They loaded several extremely precise atomic clocks onto ordinary commercial airplanes and flew them around the world, once eastward, once westward, while matching atomic clocks remained behind on the ground. When the airborne clocks were finally compared to the ones that stayed still, tiny but very real differences appeared, matching with impressive precision what the mathematics had predicted. Time once again had passed just slightly differently for the clocks that had been in motion, and at a different altitude than for the ones that had stayed exactly where they were. It seems that this isn't something limited